Good morning, students. Okay, let us move on to the next design, and it is a module number 4. Okay, so in module number 3, we have completed design of beam. Okay, it may be singly reinforced beam, doubly reinforced beam, then T beam, and cantilever beam. Okay, so now another important element of a structure is slabs. Okay, so first we'll going to see what are the different types of slabs, then we'll going to design the various slabs. Okay, so now module number 4, it is limit state design of slabs. Okay, so what do you mean by slab, and what is the main function of slab? So normally we're going to see, so whenever the large area of a room or a building, right, if it has to be covered, then it is a slab will be laid over the supports. Okay, so slab is nothing but it will be cover for the large area. Okay, so slabs are usually supported on two parallel sides. Okay, so two parallel sides, over the two parallel sides the slab will be supported, then or sometimes even on all the four sides will be considered as the support for the slab. Okay, and beams or walls are the common supports. Okay, beams or walls are the common supports for the slabs. So slab will be resting over the either beams or directly on the walls. Then generally the slab is assumed to carry the uniformly distributed load. Again, as usual, the slab is designed for the considering the uniformly distributed load coming on the slab. Okay. In most of the cases, slabs are analyzed for flexure. Flexure means bending. So remember, so normally the slab will be designed and it will be checked against the flexure bending. So there is no necessity of checking for, right, shear reinforcement. Okay, check for shear reinforcement is not required here. Only you have to check for flexure, that is bending. So with the bending moment, if you calculate the reinforcement, it is more than sufficient. Okay. Then usually slabs are horizontal. In most of the cases, slabs are horizontal, except in cases of staircases and ramps for storied car parkings. So if you take the example of large um, buildings, commercial buildings, or shopping complexes where the slab ramps will be provided, right? So this ramps is nothing but a slab, inclined slab it is. Okay, and in staircase also there will be inclined slab will be there. Okay. Otherwise, in most of the cases, it will be horizontal only. Then, what are the different types of slabs? Okay, the classification is like this. One is a simply supported slab. Okay, the slab is simply supported spanning in one direction, or it is called as one-way slab. So in detail we will going to study in the next slide. Okay, simply supported slab spanning in one direction or one-way slab. Then simply supported slab spanning in two directions. Okay, that is a two-way slab. Then third one is continuous slab. Okay, the slab which is running continuously over the number of supports is called as continuous slab. So these continuous slab may be either one-way slab or two-way slab, but it is continuous over the number of supports. Then fourth, cantilever slab. So the slab is fixed at one end and free at the other end are called as a cantilever slabs. And fifth one is flat slabs. Okay, so basically we're going to design this simply supported slab spanning one direction, that is one-way slab, two-way slab, continuous slab, and cantilever slab. So these designs we're going to do. Okay. Now let us take first example, that is one way. Now as the name indicates, one way slab. What do you mean by this one way slab? See, this is the room. Okay, so we have to cover this top of the room with a slab. Now there are two spans. One is LX and another is LY. So LX is nothing but shorter span. So what is the shorter dimension given? That is considered as LX. X means horizontal direction. Lx is the shorter span and Ly is the longer span. Okay, Lx, Ly, you have to remember, that is short span and long span. Now if you see the cross section, if you cut here and if you see when the load comes on this slab, how this slab bends. Now see, this is a slab. Before loading, this will be a horizontal, but as soon as load comes, it will going to bend like this. Okay, it will going to bend like this. So when the slab bends like this, so where the tension comes, so tension comes at the bottom. So this is a tension phase now. So to overcome this problem, okay, where you are going to provide the reinforcement, reinforcement will be at the bottom. Main reinforcement will be at the bottom. Means suppose this slab, if you want to put the reinforcement, where the reinforcement is provided at the bottom, and this is along shorter span always. Okay, in one way slab. Okay, one way means what? Right? It is the slab in which the bending takes place in one direction. Now see, this slab bends in this direction, not like this. Okay, the bending will be only along shorter span. See what you have shown. So this is called as one-way slab. So tension comes at the bottom. So the main reinforcement will be parallel to this span. Okay, the main reinforcement will be provided along the shorter span like this. 1 bar, second, third, fourth, like this. Right, throughout this span, the bars will be running like this, parallel to shorter span. That is, along the shorter span, the main reinforcement will be provided. Okay, so since the bending takes place in only one direction, this direction it will going to bend along the shorter span. This is called as one-way slab. Remember, now here onwards, one way means if the slab bends in one direction, it is called as one-way slab. Okay. So if the slab is supported on two opposite sides, now this is a slab. The slab will be laid like this slab. Okay, these are the supports for the slabs. It bends in only one direction. It will going to bend like this. Okay, as shown in figure. If the ratio of, now one more thing, if the ratio of long span to the short span, long span is Ly and short span is Lx. If the ratio Ly by Lx is greater than 2, okay, you know the long span, right? You know the short span. Take the ratio Ly by Lx. If this ratio Ly by Lx is greater than 2, then the slab is called as one-way slab. Okay, Ly by Lx ratio is greater than 2, it is designed as one-way slab. Okay, so therefore for one-way slab, longer span divided by shorter span, Ly by Lx greater than 2. So hence in one-way slab, the slab bends in only one direction as shown in figure. Therefore main reinforcement is provided along the shorter span. So it will going to bend along the shorter span. Okay, this span, it will going to bend along the shorter span. The main reinforcement will be provided along the shorter span. Okay, the main reinforcement is provided along the shorter span and distribution steel is provided at the right angles to the main reinforcement. See, main steel will be provided like this, bottom only it is, okay, like this main reinforcement, and over this main reinforcement distribution steel or distribution reinforcement is provided in the one-way slab. So distribution steel is to be provided at right angles to the main reinforcement. So remember, right? So what do you mean by one-way slab? One-way slab is nothing but the slab in which bending takes place only in one direction, that is along shorter span. Okay, then the slab is called as one-way slab. And how to identify one-way slab? Take the ratio of Ly by Lx. If Ly by Lx ratio is greater than 2, okay, Ly by Lx ratio is greater than 2, then slab is designed as one-way slab. So in one-way slab, you will going to get main reinforcement, right, parallel to the shorter span, then perpendicular to the shorter span, or over the main reinforcement distribution steel is provided here. Okay, So in slab, two types of reinforcement: main steel along shorter span and distribution steel along longer span. So this is a reinforcement. Then two-way slab. What do you mean by two-way? Now again, as the name indicates, two-way. Bending of slab will going to take place in both the direction. That is, the slab, when the load comes on the slab, if it bends along x-axis also, and if it bends along y-axis also, then that is called as two-way slab. Now see, again the same thing. This is a shorter span, this is a longer span. Okay, so if the load comes on this, slab will going to bend like this also, in this case like this also, and if you take this also, this will going to bend like this also. Okay, so the slab will going to bend in both the directions, then it is called as two-way slab. Okay, so if the ratio of, now again you have to take ratio of Ly by Lx. Okay, ratio of Ly by Lx is less than 2 now. Okay, if it is less than 2, then the slab will be designed as two-way slab. Okay, Ly by Lx ratio greater than 2, one-way slab. Ly by Lx ratio less than 2, it is two-way slab. So in one-way slab, slab will going to bend along shorter span. Okay, the main reinforcement will be provided along shorter span. And in two-way slab, the slab is going to bend in both the directions and main reinforcement will be provided in both the directions. Remember, there will be no distribution steel here. Main bars like this also along x direction and along y direction also main bars will be provided. Okay, and the total load on the slab is carried partly by short span. This short span will going to take the sum load and long span will also going to take the sum load. Whatever the total load is there, right? Major load is going to taken by the short span and remaining load will be taken by the longer span. Since it bends in both the directions, main reinforcement will be provided in both the directions. Okay, so in both the directions, the slab will going to bend, means x direction also, in y direction also it will going to bend. So main reinforcement provided along both the directions. Okay, now before going into the actual design, what are the design parameters? As I told in the previous case also, design of slab is almost same as that of design of beam. Remember, there is no much change, hardly 1% change will be there. Okay, what is that change we will going to see. First again, thickness of slab, or as usual we will going to find out the effective depth of slab. Okay, effective depth of slab, or normally we call thickness of slab. So then how to initially assume the thickness of slab? So again the same formula holds good, or same criteria we are going to consider. We have to consider effective span by effective depth here. Okay, span by depth ratio, that is effective span divided by effective depth ratio for span up to 10 meter. Okay, up to 10 meter, what will going to be? Already this table we know. Okay, in beam, cantilever beam we have taken 7, simply supported beam we have taken span by depth ratio 20, and continuous beam we have taken 26. So similarly the same table holds good here. Cantilever slab, if you are designing cantilever slab, then take span by depth ratio 7. Okay, then if it is a simply supported slab, okay, if it is a simply supported slab, then span by depth ratio will be 20. Then if it is a continuous slab, okay, the slab which is running continuously over the number of supports, it is called continuous slab. If it is a continuous slab, span by depth ratio will be 26. Remember the same table what we have used in the previous case. Simply supported 20, cantilever slab 7, and continuous slab it is 26. So these values are span by depth ratio is equal to. Okay, next, Now depending upon these values and depending upon how much percentage we are providing the steel, so these values are modified. Okay, these values are modified like this. So for one way simply supported slab, okay, for one way simply supported by slab, effective depth small d, that is span by d, is equal to 20 you have taken. So this 20 will be multiplied with modification factor. See here, so effective depth for simply supported one way slab, span divided by 20 into modification factor. If it is a one way continuous slab, okay, one way continuous slab, so effective depth d is equal to span, effective span, it is effective span divided by 26. We know for continuous slab it is 26. See this. So this 26 will be multiplied with modification factor. Then for one way continuous slab, this is both ends are continuous, one end is continuous, then it is effective depth is equal to span divided by 23 into modification factor. Okay. Then cantilever slab. So effective depth d is equal to, you have to calculate like this, span divided by 7. So 7 is a basic value. So 7 into modification factor. So modification factor is nothing but KT. Remember modification factor, what we have used in the previous case, KT, and KT value is depending upon the percentage of steel. That is, if you go to the figure number 4, IS 456 2000, figure number 4. So from that you can get this modification factor. So for one way simply supported slab, it is 20 into modification factor, span divided by 20 into modification factor. One way continuous slab, it is span divided by 26 into modification factor. Then for one way continuous, one end is continuous, other will be not continuous. Then span divided by 23 into modification factor. Then cantilever slab, okay, effective depth is equal to span divided by 7 into modification. So modification factor is nothing but KT, and this will be obtained from figure number 4 of IS 456 2000. Then the next criteria you have to consider design, effective span of a slab. So what you have done in the effective span of a beam, L effective you have calculated now in beam, same case here. Effective span of a slab. So it is least of the two. Okay. So effective span, that is L effective, will be smaller value of these two criteria. What is the first one? Effective span, that is L effective is equal to center to center of bearing. Okay, center to center of bearing. So remember, when you are designing one way slab, always you have to take the shorter span. Remember, okay, longer span not comes into picture in one way slab. So in one way slab, when you are designing simply supported one way slab, okay, the center to center distance or clear span or effective span will be always taken as shorter span. Okay, right. So first L effective is equal to center of bearing. Now see here. So if you consider this now, one way slab. So always you have to consider this span, not this, because it will going to bend always along the shorter span. Whichever is the shorter span, along that side only it will going to bend. So for span you have to consider Lx, not Ly. So now first L effective, that is effective span, is equal to center of this support to the center of this support. Okay, that is the first criteria. So L effective is equal to center of bearing. Then second, L effective is equal to clear span plus effective depth, small d. Okay, clear span plus effective depth. So there will be two values now. Out of two, which is least value, that will be effective span for the slab. Okay, effective span for the slab. Okay, as usual, same it is. Then next, bearing for a slab. Bearing means nothing but again support. The bearing to support a slab on a wall may be 100 to 150 mm. If it is not given in the problem, straight away you can assume supports or bearing is equal to 100 mm or 150 mm. Any value you can assume as a support or bearing. Next is reinforcement. As you know, in one-way slab, right, if it is bends only in one direction, okay, so along the shorter span main reinforcement will be provided. The reinforcement for one-way slab consists of main bars and distribution bars, or distribution bars are also called as temperature bars. Okay, so where you will provide main bars? Main bars shall be based on the maximum bending moment. So depending upon the maximum bending moment, you can calculate the area of steel, that is main bar, then it will be provided along the shorter span. Remember, along the shorter span only you have to provide. Then what is the area of main steel? Right, again it depends on which grade of steel we are using. Suppose if you are using Fe 415 grade steel or Fe 250 grade steel. Suppose if you are going for Fe 415 grade steel, then area of main steel, AST, okay, AST should not be less than, right, it should not be less than 0.12% of B into capital D. Okay, B into capital D. So minimum should be 0.12% of B into D. So what is the B now? B is width of the slab. Okay, B is width of the slab. And most important point, remember here, when you are designing the slab will be always designed for 1 meter width. Okay, the slab will be designed for 1 meter strip or 1 meter width. So always remember, whenever the slab design you are doing, B will be substituted as 1 meter or 1000 mm. Width of the slab will be for 1 meter strip. Okay, B will be 1000 mm. Remember, this is most important point. Don't forget in design of slab. Okay, so what is the minimum reinforcement? It should not be less than 0.12% of 1 meter into overall thickness or overall depth of the slab. So it is when Fe 415 grade steel is used. Suppose if you are using Fe 250 grade steel, Fe 250, that is a main bar, but it is a Fe 250 grade steel, then minimum area of main steel should not be less than 0.15% of B into D. Okay, it is 0.15% of B into D. Okay, next the diameter of main bars. Now which bar diameter will going to be used? Now remember, slab thickness will be always less. So hardly it will be around 150 mm or 200 mm maximum. The thickness will be less. So lesser diameter of bars will be used in the slabs compared to the beams. So beams we have used 25 mm diameter for the main bars, but here that should not be the case. Okay, the diameter of main bars may be 8 to 10 mm. Okay, either you can use 8 mm or 10 mm diameter as main bars, diameter of main bars, when Fe 415 steel is used. Okay, the diameter may be 10 to 12 mm when mild steel bars are used. Okay, so remember, if you are using Fe 415, so you can use either 8 mm diameter or 10 mm diameter bars for main steel. Okay, then what is the maximum? So maximum area of steel or maximum spacing. Now one more important thing. So when you are designing the slab for 1 meter strip, here we will not going to calculate the number of bars. Okay, so number of bars will not be calculated, but instead of spacing of bars will be calculated. In beam we have calculated the number of bars because that width was known, width of B was known. Okay, but here we don't know length of the slab. Okay, but we are designing it for 1 meter. So in slab we have to calculate spacing rather than number of bars. Number of bars will not be calculated, but spacing will be calculated. Then what is the spacing? Maximum spacing of main bars. The spacing of main bars should not exceed the following. Okay, so one is spacing 3 into effective depth of slab, 3 into small d, so that is 3d and 300 mm. So out of these two, whichever is least value, okay, whichever is least value, that will be the spacing of main bars, that is lesser of these two values. One is 3d and another is 300 mm. 3d is effective depth. Then what is the minimum? So minimum, that much we have to provide. Okay, so minimum spacing of main bars in slab shall not be less than 75 mm. So minimum, that spacing should be there, 75 mm should be there minimum. Okay, then maximum, out of these two, whichever is less, that will be the maximum spacing. Beyond not, we cannot provide. Okay, next distribution steel. This is regarding main steel. This is area of main steel. We can calculate from these two. Then maximum spacing from this. Then distribution or temperature steel. So these are provided at right angles to the main bars. So main bars will be provided along the shorter span, and perpendicular to the main steel, distribution steel will be provided. So these are provided at right angles to the main bars in order to distribute the total load and temperature and shrinkage stresses. So to take to distribute the total load and temperature, to take the temperature stresses and shrinkage stresses, these distribution steel are required. Again, area of distribution steel will be same. Whatever these are there, same. Less than, should not be less than 0.12% of B into D, and if it is Fe250, it should not be less than 0.15% of B into D. Then diameter of distribution bar. So main bars you can use 8 mm or 10 mm. Then what will be the diameter for distribution steel? Generally 8 mm diameter bars or 6 mm to 8 mm diameter bars for Fe250 grade steel will be used. Okay, so don't worry. So main steel you can use 8 or 10 mm, and for distribution 8 and 6 mm if it is Fe250 grade steel is used. Then maximum spacing of distribution bars. So spacing of distribution bars should not be more than these two. Whichever is less, that will be the maximum spacing of distribution, that is 5d and 300 mm. Here it is 3d for main steel. Okay, for main steel maximum spacing 3d and 300 mm. For distribution maximum spacing is 5d and 300 mm. Out of these two, which is less, that will be the spacing of distribution bars. Okay, then cover to the reinforcement, slab reinforcement. So in beam also you have taken the cover around 20-25 mm cover we have taken, but here since the stiffness is slab is less, so lesser cover will be assumed. Okay, so normally we assume 15 mm. So cover for the reinforcement in slab will be 15 mm. Okay, right. Or effective cover up to maximum 20 you can use. 15 or 20 will be the cover to the reinforcement. Okay, then shear. This is an important point. Remember, slab is usually designed as a beam. Slab will be usually designed as a beam of 1 meter width. Okay, width of slab will be always you have to design for 1 meter width to carry a moment over a strip of 1 meter. And in slab, instead of number of bars, okay, instead of number of bars, spacing of bars are to be calculated. Okay, so instead of a number, we can calculate the spacing of bars. Okay, so now we're going to see the steps. Okay, almost it is same as that of beam. Okay, so first step is you have to find out the dimension, that is thickness of slab. So for that, span divided by effective depth ratio you have to assume 20 if it is simply supported. If it is a cantilever slab, it is a 7, and if it is a continuous slab, it is 26. So for simply supported one-way slab, okay, is equal to span by depth is equal to 20 into modification factor. This is KT. Okay, so from this you can get the effective depth. Okay, then how much modification factor? Normally without referring a code book also you can consider. The modification factor depends on the percentage of tensile steel. So KT value is mainly depends upon what? PT value, percentage of steel. So which may be assumed. So PT may be assumed 0.3 to 0.4%. PT is equal to 0.3 to 0.4%. And for this PT, the KT value, okay, this is KT value. So KT value is 1.43, remember. So directly what I can write here is span by effective depth, or effective depth is equal to span divided by 20 into modification factor is 1.43. Directly you can remember this value, okay, 1.43. So from this you can get the effective depth, that is small d. Then add cover, effective cover 15 to 20 mm, will get capital D. Okay, so this is the first step. Second step, as usual, effective span. Okay, effective span. So two criteria, one is center to center of bearing. Okay, again take the shorter span. So in all calculation it is shorter span only, LX only. Okay, so center to center of bearing, bearing means support. Center of one support to the center of one support will give L effective. Then another will be clear span plus effective depth. Clear span plus effective depth. Effective depth, this whatever you will going to get, add this. So out of these two, which is the least value, lesser value, that will be L effective, that is effective span. Okay, this is second step. Third step, total load. So as usual, first load is dead load of the slab. Okay, dead load of the slab will be B into capital D into 25. This is density of RCC. So what is B? B is width of slab. How much width of slab? It is 1 meter. Remember, B will be 1 meter or 1000 mm. Then D will be capital D. That is the overall depth of the slab or overall thickness of the slab. 25 is the density of RCC. That is dead load of the slab. Then dead load of the floor finish. So above the slab. So suppose if you are providing the tiles also. Okay. So that load will be considered. That is called as floor finish. Okay. So approximately we can assume 1.5 or 1.2 kilonewton per meter. Then live load, it will be given in the problem. So write down that kilonewton per meter. So add all these three. Dead load of the slab, dead load of the floor finish and live load. So we'll get total small w. It is UDL. Small w means it is a working load. Multiply this with 1.5. We will going to get the right factored load. WU you will going to get. Next you have to calculate bending moment and shear force. Right. So it may be one-way slab or it may be two-way slab. Okay. Right. Suppose if it is a one-way slab and it is simply supported slab, simply supported, then what is the maximum bending moment? Same, WL square by 8. Okay, at the center of the slab, maximum bending moment will be WL square by 8, and maximum shear force at supports, it is WL by 2. WL by 2. Already we know this for simply supported maximum bending moment and for this maximum shear force. Then check for effective depth as usual. Equate mu is equal to mu limit. Okay, so whatever the mu you are calculating here, equated this to mu limit. Mu limit again depending upon the grade of steel. Suppose if it is Fe415, then it is nothing but 0.138 FCK BD square. So from that, check how much D is required. So suppose here D required is 150 mm, and in the beginning what we are calculated here, this, if you are calculating this 180, you are providing 180, then it is safe. So whatever you are providing, that should be more than required. Okay. Now in this equation also, B you have to substitute 1000 mm. So wherever B is there, don't forget to substitute 1000 mm or 1 meter. Next, once if you get the bending moment and shear force, next to take this bending moment, you have to calculate area of steel, main steel it is, area of main steel, that is percentage you have to calculate first. Again substitute, use this formula, substitute B is equal to 1 meter, remaining it is same. So we'll get the area of steel. Okay, so percentage you will get first, then area of steel is equal to PT by this PT divided by 100 B into D. Again B is 1000 mm. Then as I told, don't calculate number of bars here. So calculate spacing of bars. So how will calculate spacing of bars? For 1 meter, for 1 meter width of slab, what will be the bars spacing? Okay, bar spacing we have to calculate. So how will calculate spacing of bars is equal to area of 1 bar divided by total EST. Now it is reverse now. When you are calculating number of bars, okay, what you have taken? Total EST divided by area of 1 bar. But here when you are calculating spacing, it is area of 1 bar divided by total EST into 1000. Why it is 1000? So this is because of 1 meter we are calculating. Okay. So area of 1 bar. Suppose we are assuming 8 mm diameter main steel. So it is pi by 4 8 square divided by total EST. What we are going to get from this? Multiply by 1000. So in 1 meter you are calculating. So spacing you have to calculate. Next, distribution steel. Okay, next will be distribution steel. So either see the grade of steel. You are using Fe415 or Fe250. If you are using Fe415, so calculate EST, area of distribution steel, AST D. D means distribution steel. So 0.12% of gross area, B into capital D, if it is Fe415. If it is a Fe250 grade steel you are using, then it is 0.15 B into D. So from this you can calculate area of distribution steel. Then again as usual you can calculate the spacing. Okay. Next is check for shear stress. Normally in the slab, okay, always that shear stresses are not coming, and especially the stirrups are not required, or shear reinforcement is not required in slab, but in beam it is required. So anyhow that you have to check. Okay, check is a must. So nominal shear stress tau V, that is VU upon B into D. So B is nothing but again 1000, remember. So again for solid slab, the design shear strength or permissible shear strength of concrete shall be calculated. Now in the previous case you have only calculated tau C. Now here in the design of slab, tau C value whatever you are going to calculate, that will be multiplied with K. Okay, so when we start the problem, how to calculate this we'll going to see. But right now remember, tau C you have to calculate as usual depending upon the percentage of steel. Then that tau C will be multiplied with K. Okay. Now compare tau V and K into tau C. Tau V and K into tau C. If this tau V is less than K into tau C, okay, the slab will be safe in shear reinforcement, or shear reinforcements are not required. Okay, suppose in case tau V greater than tau C, K tau C comes. If this is more than this value, then you have to go to shear reinforcements are not provided here. Remember, okay, shear reinforcements are not provided because this is slab thickness is very less. We cannot provide the stirrups are not provided here. So if tau V is greater than K into tau C, straight away directly you have to redesign now. Again go back to the first step, assume span by effective depth ratio some other value now. Again repeat all the steps, but it is not case. Okay, always this step will be automatically satisfied. Okay, so if tau V less than K tau C, your design is safe. Okay, right. Next, after this, okay, you have to draw the sketch showing the reinforcement detail. So remember, what is the major change between design of beam and design of slab? So in slab, right, the slab will be designed for 1 meter width. So always width of slab will be, small b will be 1 meter or 1000 mm. Okay, so that you have to remember. Then span by effective depth ratio, whatever that value is there, 20 you have to multiply it with modification factor, or if it is a cantilever slab, it is multiplied 6 with modification factor. So like this we have to calculate the, or we have to design the slab. So remember, main reinforcement along shorter span and a distribution steel along longer span. But always remember, main reinforcement you have to provide first, over that you have to provide the distribution steel. That you have to keep it in mind. So when you start with a problem, automatically once again we're going to repeat all these steps. So I hope you understood this. Please go through all these steps. Okay. So in the next class we'll start with the actual design. That is, first we'll consider simply supported slab. Okay. Simply supported slab. Then we'll start with the cantilever slab. Then last, continuous slab. Okay. Thank you very much for attending this session. Have a good day.